Picture this. We have a stock exchange with 1,000 listings. Every year, 5% or 50 companies have credit events, such as outright bankruptcy or coupon default. Now assume you have a machine learning binary classifier which you believe has some ability to predict credit events. You run the model for one of your investments, ABC Limited, and it says this company will default. How confident do you feel about this? Should you act on the model's result by immediately selling your shares in ABC? We are going to look at the confusion matrix in this video, a powerful tool to evaluate what your machine learning algorithm predictions mean and whether you should trust them. Let's see how we can use the confusion matrix to gain a deeper understanding of our model's performance. For a binary classifier model, a confusion matrix is a simple 2x2 table with 2 columns and 2 rows. We will label the columns as actual. By that we mean that is the true state of the situation that we are looking at. You may, if you are reading around about this, see that referred to as the ground truth. In our example, we are looking at situations in which the company actually does have a credit event. Then we will label the rows as predicted, by which we mean the model's output. Next, we label the 2 columns and the 2 rows as positive and negative. And in doing so, we are going to be a little bit careful in terms of our understanding of what positive and negative mean. In this case, we have positive defined as a credit event, which means in a plain language sense that it is not a good thing. So you need to be quite careful about your reading of a confusion matrix in the sense that you will not fall into the error of making the assumption that positive is some kind of good outcome. More often than not, in finance, as well as other situations where machine learning is used, a positive result is, on the contrary, not a good thing. Next, we label the 4 quadrants of our table, starting with the true positives. Here we have situations where the actual class is positive and the model also predicted positive. In our example, we are looking here at situations where the company actually does have a credit event and the model predicted exactly that. Moving to the bottom right, we have the true negatives. And here, once again, we must be a little bit careful in our interpretation, and we need to be clear that the negative in this case is in fact a good outcome, because a negative result means that the company does not have a credit event. It does not default. So the true negatives are situations where the company does not default and the model predicts exactly that outcome. Moving on to the false negatives at the bottom left, these are situations where, in our example, the company does default, and yet the model predicted that the company would not. So we have a defaulting company which is identified by the model as being absolutely fine. Moving to the top right, here we have the false positives, and here the company does not default, and yet the model predicted that it would. So once again, I think that underlines that you need to be quite careful and read your confusion matrix or set it up very carefully indeed. Before we carry on, let's add some fairly obvious acronyms which will be useful to us when we start working with the equations for the various evaluation metrics that we extract from the confusion matrix. Then let's do the column and row totals. We will use P and N to represent the total actual positive and negative outcomes. And I remind you that those are the actual or true or ground truth or real state of our population of interest. Then we will label our row totals with P star and N star. which are the total predicted positive and negative outcomes. And then at the bottom right, we have the total number of observations, which is p plus n, or equivalently p star plus n star. A final comment to end this video about the orientation of the confusion matrix. There is no standardized orientation, and I think you need to know that. In the version that I used in this video, I placed actual along the columns and predicted along the rows, but that orientation could easily be switched depending on the source that you are looking at. And furthermore, I also chose to place positive as the first column and the first row, but of course you might encounter situations in which negative is the first column and row. And there are, in fact, another 4 orientations that I've not shown on that particular slide that I'm not going to talk about, and those are situations in which the positive negative order of the actual and predicted outcomes are inconsistent across columns and rows. But perhaps the 4 most common situations that you might encounter are shown on the screen right now, and that just underlines once again the importance of being very careful when you read or set up your confusion matrix. And that's it for this video. In the next one, I'm going to do a worked example in which we take some numbers and equations and we calculate various metrics which tell us how the model actually performed and whether we should trust its results or not. And thank you very much for watching. I applaud your persistence and enthusiasm if you made it this far, and I will see you in the next one.